So in this lecture, we continue discussing integral extensions, and we first prove a statement about transitivity of integral extensions. Okay. So here is the proposition. So it has some 4 parts. Let R to S and S to T be finite. So this is part 1, be finite extensions. Finite, or let's be consistent with our terminology, finite morphisms, ring maps. So as a module over S, as a module over R, S is a finitely generated R module and T is a finitely generated S module. That's what. Okay. Then the composite map R to S is finite. S is a finite composite map, R to T is finite. T is finitely generated R module through the composite map. Okay, so this is the first statement. 2. Let S1 through Sn inside S. So now R to S is some ring map, and S1 through Sn inside S integral over R. Okay. Then the subring generated by R and these elements. So by this we mean the image of R inside S and these elements, but we will stop writing it once we get used to this thing, is a finite R algebra. In other words, it's a finitely generated R module. 3, same as the first statement, but now for integral. R to S, S to T, integral extensions. Okay. S is every element of S is integral over R, and every element of T is integral over S. Then the composite map R to T is integral. Okay. And 4, the set of S inside S such that S is integral over R is a subring of S, containing R. Okay, sorry. Okay, containing the image of R, containing image of R. In other words, it's a R subalgebra of S. Okay. So let's just look at the statements. First statement is that if you have 2 finite morphisms, then the composite is a finite morphism. Second statement is if you have a ring map and some finitely many integral elements, then the subalgebra generated by that finitely many integral elements is actually a finite R algebra. This is only finite type. Okay. A priori, this just means finite type. But because these are integral elements, it's actually finite. Okay. And third is, if you have 2 integral elements, the composite integral extensions, the composite is also an integral extension. And third, final is the set of integral elements inside a subring, inside a ring, is actually a subring. Okay, so this is called, so this is a thing, this is called the integral closure of R in S. Okay, so we'll come back to that in a minute, but let's prove this. So I'll okay. So proof. One is an exercise because it's done. This is exactly how one would prove that if you have two finite extensions of fields, then the composite extension is a finite extension. Okay, so this is the same proof, just repeat it, with appropriate changes of words, and you'll get this. So first one is an exercise. So the second one, second one, we want to show that R adjoint S1 through Sn is finite. So this is what we want to show. Okay, but we can use 1, right? So we can start with R, then we have S1, okay, and then we have R, S1, S2, and so on, and then we have all of them. Okay. This is finite because this is finite, suppose we prove that individual ones are finite, then the composite is finite. So, okay. Now just one more observation. S2 is integral over R, hence it is integral over this intermediate subring also. Similarly, any Si here is integral over the subring generated by R and the previous elements. Okay. So at each stage, it is just adjoining one integral element. Okay. So by induction, okay, and 1. So if you prove that each extension here is finite, then the composite is finite. So then by using 1. So by induction and 1, we may assume that n equals 1, and let's write, okay, and let us write yeah. Okay, so now let's go back to the previous proposition. Okay, so we are just interested in so S1 integral over R. Okay, now let's go back to the previous proposition. The proposition from the previous lecture. So this now implies that R adjoint S1 is finite over R. Okay. So in the previous lecture, we found various conditions for equivalent to an element of an extension ring being integral over the base ring R, one of which was that the subalgebra generated by that element is a finite algebra. Okay. So this proves 2. So now 3. So 3, we need to prove that every element of T is integral over R. So let T be inside T, and we want to show that T is integral over R. Okay. We know that T is integral over S. So let S1 through Sn be inside S be such that T to the n plus some Si T to the n minus I goes from 1 through n is 0. This is because T is integral over R, T is integral over S. Okay. Now consider the subring generated by, so let S prime be the subring of S generated by R and S1, S2 through Sn. Okay. So this is the subalgebra. These are integral over, okay, so S1 through Sn are integral over R. integral over R. So S prime is finite over R. Okay. Now T, this element T here satisfies an integral equation over S prime. So T, the subalgebra generated by S prime and T is integral over R. Okay. So this is finite over R. So now this now implies that T is inside some finitely generated, some finite, okay, okay. So now look at the extensions R inside S prime. This is finite, and this is S prime and T. This is finite. That is because T is integral over S prime. Composite of two finite is finite. So therefore this is finite. Okay, and okay. So therefore S prime T, S prime adjoint T is a finite R algebra, okay, containing T, okay, which now implies that T is integral over, again going back to the first proposition, T is integral over R. Okay, so this proves third, that integral extensions, the composite of two integral extensions is an integral extension. Okay. So now for 4 we need to show that, so we'll write R bar for that set. S inside S is integral over maybe let's just call it A, integral over R. Okay. So we want to show that for all S1, S2 inside A, S1 plus S2 is inside A, and minus S1 is inside A. Okay. So let's look at, or in other words, S1 plus S2 is integral, and S1 is integral. S1 is integral, S1 plus S2 is integral, sorry, S1, S2 is integral. Okay. Sums and products. Okay. So now let's look at these extensions. So we start with R, okay, then we adjoin S1, and then we adjoin S2, S1, S2. Okay. These are S1 and S2 themselves are integral. So this is finite. This is also finite. Okay, and S1 plus S2 and S1, S2 are elements here. So these are elements inside a finite algebra. So therefore they are integral. S1 plus S2 and S1, S2 belong to a finite algebra, finite R algebra, so they are integral. Okay, so this proves the theorem, this proposition. So what it says is composites of finite is finite, composites of integral is integral, and it also proves, makes this 2 is the other thing, that if you have a finitely generated algebra, okay, generated by integral elements, then it is actually a finite algebra. Okay, so that's 2. And final statement is the integral closure of a ring in another ring is a ring. Okay, so we'll define this integral closure definition. Let R to S be a ring map. Okay, the set, the ring which we just proved, it's an R algebra. S inside S S integral over R is called the integral closure of R in S. Okay. And we say that R is integrally closed in S if its integral closure in R in S is R itself. Okay. Just one observation: when we say this is integral closure, it should, at least in principle, suggest that if something is integral over this ring, it's already integral over R. Only then you can think of it as a closure. Okay. So that when you apply that operation twice, you do not get anything new. So which is indeed true. The case is indeed true. Suppose that there is some T inside S which is integral over this ring. But then we go back to the previous proposition to conclude that T is integral over R, which means T would have been in this set. Okay, so it's indeed a closure operation. Okay, so just one more definition. Let R be a domain and K its field of fractions. Well, we don't need a name. Okay, the integral closure of R in its field of fractions is called the normalization of A. Normalization of R. Okay. So this is definition. We will not worry about normalization exactly at this point, but we will develop more about rings, integral extensions. Okay. But we can nonetheless look at one example. Z is integrally closed and the field of fractions of Z is rationals, and so it's integrally closed in Q. Okay, so how do we do this? So let A over B, the fraction, be inside Q, be integral over Z, and assume without loss of generality that their co-prime integers, that is their GCD, is 1. Okay. So then we have A over B to the n plus some integer C1 times A over B to the n minus 1 and so on, Cn equals 0 for some integers C1 through Cn. This is what integral means. Okay. Let's multiply by b to the n. So then we would get a to the n plus there will be a b, there's only n minus 1 copies of b here. So when we multiply, we would have a b there, and everywhere we would get a b in all these terms. So some b times some c prime is 0 for some integer c prime. Okay. Now, what does this say? This says that a to the n is in the ideal generated by b. Okay. Now, if b is 1, there's no issue because this is true. And if b is 1, then a over b is in z. Okay. If b is 1, then we are okay. A over b is actually inside z. Okay. If b is not equal to 1, then let p be a prime divisor of b, prime number dividing b. Then this one says that a to the n is in the ideal generated by p, because these are, it's inside b and p is a maximal ideal containing b. Okay. Which now implies that p divides a. But then this contradicts the hypothesis that a and b were chosen to be relatively prime. Okay. So you can essentially rehash this argument to prove that every UFD is integrally closed in its field of fractions, which you will do in their exercises. Okay. So let's look at another example. So this is, the same argument will prove that polynomial rings are integrally closed in their respective field of fractions. Okay. So, but here let's consider something slightly different. xy over y squared minus x cube is not integrally closed. In its field of fractions. Okay. And the easiest way to understand that is to rewrite this as something that we have seen earlier. So note that this ring is k t square t cube. Okay. So the field of fractions contains t. Fractions is k round bracket t, a rational function field in one variable. Okay, because t cube over t square is, okay, so notice that t is y over x. Y over x. Okay, so that is inside here. Okay, and t is there in the field of fractions, and t is integral over this ring. T satisfies. So let me just use a different variable now. Z square minus t square equals 0 over k t square t cube. Okay. This t square is from here, this z square is a variable, and that is where we substitute t. Okay. So therefore, k t, if you take k t square t cube, this sits inside k polynomial ring t, sits inside k round bracket t. Okay. This is an integral extension or a finite extension, and this is integrally closed here. That is essentially that UFDs are integrally closed. One can just redo the argument for Z in this case. Okay, so we have three. This is the field of fractions. Between this and the field of fractions, there is this ring. It is integral, and that is integrally closed. Integrally closed in its field of fractions. Okay, so this is the picture for this one. Okay, so we can just Okay, so in other words, I mean, this element here is in the field of fractions because of this. These are not just, I mean, here this y and z are not variable, there is a relation among them. Okay, so now we come to one of the results that I informally mentioned earlier, which is that given any finite type algebra over a field, there is a polynomial subring over which the field is, over which the algebra is finite. We only mentioned about maps between spec, but this is a slightly stronger, this is a stronger statement, and this we will prove not immediately, but right now we will use it to derive, to draw applications, one of which is, the main part of which is to prove the Nullstellensatz. Okay? So this is, so before we state the theorem, we need a definition. So let K be a field and R a K algebra. Okay, so definition: Z1 through ZD inside R. For the definition, we don't need to assume that it's finite type, but we are taking finitely many elements inside R. Okay, is said to be algebraically independent if algebraically independent over K. Okay, so let's just say what we are saying. So K to R is a ring map, and here we have taken some element Z1 through ZD. Okay, so we have seen this earlier, that if you have a ring map like this, then it extends to a map uniquely from a polynomial ring over K, mapping the variables mapping to this, and scalars mapping accordingly, however this was getting mapped. Okay, so over K, sorry, this is just if the map from K x1 through xn to R, xi going to zi, so these are variables, okay, is injective. So the map extending the given map K to R. So always this is one of the first few lectures. We are given a map from K to R and a bunch finitely many elements. So that is the, so maybe I should just say this is a polynomial ring. Okay, so that extends to a map from the polynomial ring to the same R itself, extending the given map. Okay, so this is given is injective. Okay, in other words, the algebra generated by Z1 through ZD and K inside R is a polynomial subalgebra. Okay, so we say that this is a algebraically independent. They behave exactly like variables. Okay, so in other words, K Z1 through ZD inside R is a polynomial K subalgebra. There are no algebraic relations among them. That's what algebraically independent is. Okay, so here is what is the theorem called Nether normalization. The same Nether as Noetherian, Emi-Nether. Lemma. Okay. Let K be a field R a finitely generated K algebra, then there exist algebraically independent Z1 through ZD such that R is finite over the subalgebra generated by the Z's, which is a polynomial algebra. Okay. So this is the theorem called Nether normalization lemma. Okay. This has lots of applications in various contexts, studying rings that are finite type of over a field. We will not prove it right now. We will first draw some corollaries from this. First draw one corollary from which we will prove the one version of the Nullstellensatz.